Okay, hello everyone. Thanks for coming to our Halloween science demonstration show. Just a show of hands real fast, how many of you guys like science? Ooh. We got almost everyone. Well, those of you who didn't raise your hand, I hope that we can convince you to like science today. So I'm Mr. McCormick. I teach science over at the high school across the street. And I brought a few awesome science students who are going to come and do some cool science demonstrations for you. One thing you'll notice while they're doing this show is that everyone is using the proper safety equipment. They'll all have aprons, goggles, and gloves on so that they can be safe while doing science experiments. Safety is our #1 priority here. You will see a few science demonstrations that you can do at your home. But there are other science demonstrations you'll see here today that you should only do with a trained scientist with you. Anyways, we're going to let our first group take over. They have a chilling Halloween skit to perform for you.
Hi there. Hi there.
Oh. Testing.
Cool. Thanks. Hi there. My name is Draven. We have here a wonderful science presentation about a chemical called liquid nitrogen. Have any of you ever heard of it? Does anyone want to say anything about it? That is right. We were going to do the ice cream thing, but it'd be a lot of ice cream, right? So we're going to do some other demonstrations with the things we have set here. I need an assistant, though. I need to call upon one of my old friends. I'm sorry. By this spell, I command you to rise, spirit of Halloween. I need help from you and your assistants to help me with this liquid nitrogen decoration for my party this year.
A Halloween party?
Yes, that is the kind.
Whatever it is you ask for. By the power of this hand, associates of mine, come forth, I say, and serve your master. Raccoon, Pawn, wonderful to see you again.
Indeed, how may I help you?
Yes, my friend here is in need of helping prepare for a Halloween party. Yes, and we shall start with that canister there. What's in this canister anyway?
Liquid nitrogen.
Yes.
I was just telling all my friends about it.
And what does liquid nitrogen do?
Well, in retrospect, it freezes things.
Wonderful. 'Tis the season for bitter chills. We shall start with that duck there and put it in that cauldron there.
Yes, sir.
But wait.
Why do I need these?
You don't want to freeze yourself, do you?
No, senor.
Good. Now, off you pop. In the meantime, I shall make sweets. Pour me a glass, please. Thank you.
Double, double toil and trouble. S'mores freeze and cauldron bubble. The spell might take a bit.
Very time consuming.
As hard as a rock.
What a magical achievement. Easy. The temperature of liquid nitrogen is around, let's see, negative 200 degrees. So therefore, it freezes anything it touches.
Don't forget, we need decorations for my party.
Of course. What party is complete without decorations? Akun, hand me the pumpkin.
Hocus pocus zibbity zam, freeze this pumpkin by my command.
Thoughts?
Chillingly wonderful.
The guests are sure to get hungry, will they not?
Of course. And to that, I shall add fruit.
Just one?
Listen, my magic can only get us so far, okay?
Or rather, one half.
More, I say, more. That's good. Thank you.
Can't get a grip on it.
Nope. Very slippery. Potassium!
Do you have anything else in your coat?
Don't touch it with your bare hands.
Very cold, I tell you. Aha! A hand!
And why?
Enough questions.
A rose?
Oh, a wonderful centerpiece.
Yes, and for that, it must freeze.
This is my favorite part.
It does take a while, though. Be a dear and move the pumpkin for me. Other pumpkin. Ah. I think it is done.
I believe so.
And in 5 minutes, the guest should arrive any second now.
Scarecrow,
Yes?
what day is it today?
Thursday, why?
My party was on Wednesday.
All right, wasn't that awesome? We got to see the amazing freezing power of liquid nitrogen. All right, our next group here is going to show you a very interesting chemical that looks a lot like water. I'll let them explain.
Hello and welcome to our presentation.
Could we get a volunteer from the audience? You, come up here. Put one packing peanut in there. Can we get a hand for the volunteer? As you can see, this is no ordinary liquid.
As you can see, I have a whole boat in my hand.
I will destroy the world. Man, I'm getting kind of thirsty. Could you pour me a drink, pal?
Of course. Whoops.
Oh my goodness! I forgot about my close friend Stan. Here, Stan. I'm gonna put you right here in this empty bowl. So Stan and I here have been the closest of friends since, like, forever, you know? Stan and I have just been the bestest of friends, and I love him so very much with my whole heart. If I had two hearts, hold on, I'm talking about Stan here. Stan and I, honestly, I just love him so much. He has just been the bestest of friends I could ever ask for. And honestly, if he were just to die right in front of me,
Stan!
Stan? Stan? No!
Okay. So, okay. This is a Okay. If we could quiet down, we can finish this demonstration. Thank you. This is a process where this liquid called acetone breaks down these objects which are made out of styrofoam, which the styrofoam has air pockets in, which the acetone can get into the particles and break it down really easily. It makes the styrofoam disappear, but wait, it doesn't just disappear, it changes into a different form. They're squishy right now because they aren't dry. But once it hardens, it turns into this solid rock.
All right. Okay. All right, everyone. Let's give another round of applause for our science demo group up here. All right, our next group is going to show you how to do a really easy at-home science experiment.
Alright, hi, I'm Emma and this is my assistant.
Hello, I'm Hunter, and this is my partner.
He's my assistant.
Partner.
Today we're going to make a homemade lava lamp. So we're gonna pick up 3 people. You.
Okay. You with the red shirt in the back. No, other one next to you. Yes, you. Get up here.
Hi, buddy.
Yes. No, you. Come on. Come on. Bradley, I know you can see me. Okay.
Can't pick any.
Where the crap are you?
Come on, you gotta pick 4 at least. You come.
Yeah, I know. Where this kid come from?
You.
Brandon, I didn't know this one either. Where do these two random?
So confusing.
Where are all these random kids coming from?
I am now You've taken forever to call them.
I don't.
Alright, we got 4.
Congratulations.
Congratulations.
Thank you. Bye. Shoot.
No, you ran off. Come here.
Ah.
No?
The
No,
other
we need
kid-
one more.
Pick him, Dalton. Yeah,
Him?
Yeah, right.
Okay.
Hello, Dalton. This is my sister.
Now there's 5. Wow.
My annoying sister.
Okay.
I didn't even know
Yes,
this.
we do. Wait, I've got the most important part.
Oh, no.
And you can't have a show without it. Just light
If
it.
you can
come
do
on.
it. If you can do it, don't worry. Just can't do it.
All right, I
You
give
can
up.
use that one.
Okay. So you can pour in the water. You have to be very careful. Uh-huh. You'll pour in half of it, and you'll pour in the other half.
Yay.
Alright.
I'm gonna pour half.
You get a food dye,
Yay.
and then you get 2 Alter tablets. And you get 2 Alter. I'm dropping stuff.
Why are you dropping?
I'm a professional, okay? And then you can do the oil.
It's the ice cream.
All right. We're gonna start with the water. So if you want to pour it in there.
I'm not good at pouring. So is water called oil?
Well, your time has come.
Oh,
Be very careful. Don't dump it all in at once.
this time. I remember this. It made smoke. I need my mom to pick me up. This is scary.
All right.
Okay.
You can do the food dye.
Scary and epic at the same time.
5 drops.
That
Said
is not
5,
fun.
child.
That is not 5. 10.
Okay, we're
That
good
is
here.
not 5.
Okay,
That
no
is not
more.
5. That is not 5.
Okay.
That is 20. My sister made it plan hard.
Back up. All right, you can pour in the oil.
Now you have to put a scoop in.
Yeah, I gotta put in that cheese. Ready?
Pour the whole thing. The whole
Oh, slow down there.
Hold it. Slow it down. Put the whole thing in. Whole thing. The whole thing in, Patrick.
Keep pouring. Keep pouring.
Is that apple?
Wait, slow down.
Patrick, whole thing, Patrick. Is that apple?
Slow down. Stop at that.
Is that oil? Good point.
Keep going. That's good.
Well, turn.
A lot of oil. Okay, yeah, you go ahead.
Can I pour a little bit more?
No, you can't.
No.
What else? Drop the ounce.
All right, y'all can go back to your seats after he puts in that.
I can't be back.
You want to put in there?
I think I know what's gonna happen.
Okay,
Bubbles.
there's the lava lamp.
Okay, now all of you can leave.
I want to eat another. Can I eat a marshmallow?
No.
Go sit down. All right, everybody back to your seats. All right. So, this is how it works. The pill that he just put in
I said
makes bubbles, and it starts in the water, and the bubbles float up through the cooking oil. Since cooking oil is actually a heavier liquid, the bubbles will appear into the water and start to escape for air and get stuck in the top to escape slowly, which makes it rise up. In shorter terms, oil can't mix with water. All right. Oh yeah, one more fact. This is actually, we came up with the cure to everything.
What
So,
is this
it's
garbage?
very important. This is the cure for everything.
Oh, what is it? Does it cure everything?
Yes, it does.
Oh, yeah?
Pick it up.
I'm sorry. I'm
No,
sorry.
give me your money
I'm
until
sorry.
you pick it up.
I'm sorry.
Give me $5. $5.
Okay.
Yeah. You won't rip my stuff. Jeez.
Here's the money. Right here.
Trust
Okay.
me.
Down here. I hope nothing happens to my dollar. I need that to get home.
Hold up and just figure this out. Oh, there you go.
My money! No! Oh my gosh! My money! That's my... Ah! Oh my god!
Let's go get the marshmallow.
I need this to
get home.
Go get the marshmallows.
Oh, wait.
Where's the marshmallows?
Yeah. The money's okay. Woo! The money's fine. So, the thing they put it in was alcohol, which burns, right? Okay, and then they added a little something extra, water. And I don't really know how it works. I'm kind of stupid. But I guess the water stopped it from burning. So it's okay. Thank you. This is science.
All right, guys, how many of you out there like blowing bubbles? Excellent. So our next group here is going to show you how to blow some special Halloween bubbles. Okay, go ahead.
How's everybody doing tonight, eh? Awesome. Well, we're going to be making something called Boo Bubbles. Pretty fun, right? All right, so first things first. First things first, we gotta make sure that y'all know that we're gonna be using dry ice, and if you're not careful, you can get freezer burn. That's not right. So always use thick gloves, yeah. All right. So first of all, we're gonna need a whole bunch of things. We have this jar here. We got a tube on it so that we can, get the gas out so we can blow the bubbles. We got some warm water here. We got some soap mixture, just with some water. We got the dry ice. First things first is we gotta get the water into the jar, yeah. After that, we gotta get the dry ice. Cool, huh? This is called sublimation because carbon dioxide is so cold it can't exist out of fluid when it gets warm, so it goes straight to a gas, which is what all this fog is. After that, we're gonna screw this lid on. Make sure it's coming out the other end, and then we're gonna dip it into the soap mixture. Can we have a couple of volunteers to come blow some bubbles? Come on. Yeah. Come on. Then, you. Yep. And you. Want to go on? Awesome, right?
I don't mind. Safety first. Oh boy, I love science.
Okay, so if you notice, they didn't pop immediately when they hit the towel. The reason that is because the towel doesn't have any oils or dirt on it like our hands do. So they didn't pop immediately because the outside of a bubble is made of soap. And soaps break down oils and dirt. And so they become unstable, and then they can't have that surface tension that bubbles need in order to stay as a bubble. Also, you probably noticed they didn't float, they sort of fell. The reason that is because the gas inside is carbon dioxide, and that's a lot heavier than just the air that we breathe in and out, because that's a whole mixture of carbon dioxide and a whole bunch of other gases. So it's gonna fall and it's gonna be there. That's why you have this towel down so that they don't pop immediately as well.
It's way too cold. No? And it's way too cold. I would suggest it. My brother did that once. Don't pop it. Yeah, it was fun. But he kind of overdid it. Hey, Jason. Oh, that's hot. It's hot.
Well, anyway, that was Boo Bubbles. Hope you enjoyed the rest of the show.
All right, how many of you guys have seen a chemical reaction happen before? Ooh, quite a few of you. Can anyone tell me what to look for to know if a chemical reaction is happening? Who knows what to look for?
Yeah, I'll put it on.
Bubbles.
Ooh, bubbles. Yes.
A reaction that can happen over or cannot.
Oh, okay. Over and over, repeating itself.
I'd have to say something really unusual.
Something really unusual happens.
Elephant toothpaste.
Ooh, elephant toothpaste.
Smoke.
Smoke, I like that. Okay, one more.
A white gas.
A white gas. Those are all some great things to look for when you're trying to figure out if a chemical reaction is happening. Some other things that we can look for is a change in color. If you see a color change, or if you see bubbles, or maybe if it gets hot, or even if it gets cold. Our next group is going to show you a really cool, easy to do at home chemical reaction, but they've added a little Halloween twist to it.
So we're going to be making elephant toothpaste in a pumpkin.
I'm going to be dumping hydrogen peroxide into the pumpkin. Well, hydrogen peroxide is made of hydrogen and oxygen atoms.
Okay, next I'm going to add dish soap to make more foam in the experiment.
I'll be adding food coloring so that it will be striped when it comes out of the pumpkin.
We're going to add the yeast next so then it activates it.
It's so chunky.
All right, let's give a round of applause for the elephant toothpaste in a pumpkin. Okay, elephant toothpaste works. Did you guys already explain it? Yeah. Elephant toothpaste works because it's giving off a gas, and that gas is getting trapped inside of bubbles. Another type of chemical reaction is one that produces heat, and there's also some that take heat. Our next group is going to show you one of these chemical reactions that take in heat.
What's up, everyone? We're going to do a little demo here for you guys today. We have two reactants. One of them is barium hydroxide, and it's a white crystalline solid. It's right here. The crystals are fairly large, and it's kind of shiny, and we have 64 grams of it.
The second reactant is ammonium chloride, and the formula is NH4Cl, and we have about 22 grams of that, and it's right here. It's this. So now that we have the two white solids here at room temperature, Tate is going to be mixing them together in this, that thing, beaker. And it's gonna be, we're gonna put it on the piece of plywood right there, but before that we're gonna put distilled water on it for the experiment to work.
So now that we have the water and the beaker, I'm going to add the two reactants. First is going to be the barium hydroxide. And then second is the ammonium chloride. And I'm going to be mixing them with this thermometer right here.
Right away, there's a very strong scent coming off of it, and that's due to the ammonium chloride producing ammonia and other And the other observation is that the thermometer is going down, the temperature is going down rapidly because it's getting colder and colder by the minute, by the second.
All right, so I'm going to keep mixing this, and you can see that there's somewhat of a liquid solution in the bottom. It's almost like snow, but don't eat it because that's why our other partner isn't here today.
Yeah, that was. Don't talk about him. He's gone.
But this reaction creates water. That's why it looks liquidy. This experiment takes a little while to work, so how was your guys' day? Was it good? Good? That's good.
Like bananas? What's your favorite experiment so far? The one that you got to volunteer in? Oh, you like bananas? Me too.
Say,
what's the temperature?
Say ours has been pretty good. Say that.
Ours has been pretty good too. You know, we got to watch all of our fellow classmates do their experiments and got the prep for this. It's been pretty fun. Read the temperature.
The temperature is now at negative 16 degrees, so it's really cold. And
it's starting to look more like a liquid now, and it's very liquidy, and it's very, very cold to the touch.
all right, by now it should be ready. We're done. So, let's see. Ta-da!
It worked.
Wow.
And yes, the beaker is stuck to the board. This reaction is very well an endothermic reaction, meaning it absorbs the heat from the surroundings. It's so good at absorbing the heat that it absorbs the heat from the water, freezing it solid, connecting the beaker and the board together.
Ta-da!
And that was it.
Hey group, before you go, there are a couple of kids that look like they have some questions. Do you mind trying to answer a question real fast?
Yeah, we'll try and answer a few.
Okay.
Pick on some.
There. It's pretty strong.
Pretty strong. I could try and pull it apart, but I'll probably break the beaker, so. Yeah.
You.
Pretty strong.
That one.
So the reaction between the two chemicals gets really cold, so it freezes the water, connecting the board and the beaker together.
The chemicals react. It's the solutions in them, like the way the formulas in them. We don't really know much about that, but they just turn really cold.
Yeah, science.
Science.
It'll stick to the board for probably like another 5 minutes. It's still fairly cold. I'll check.
Kid in the white shirt, right there. Uh-huh. What type of powder? Is that what you said? Oh, it's very chemical. You don't want to touch it with your bare hands because it's very harmful, right? It's
toxic.
Yeah, these two chemicals are kind of dangerous. We have, what was it again?
Ammonium chloride.
Ammonium chloride and
Barium hydroxide.
barium hydroxide. These are dangerous chemicals. If you get them on your skin, then they'll cause rashes and even burns. So this is why our group up here is wearing gloves and aprons and goggles to keep themselves safe while they're working with them. All right, so we saw a chemical reaction here that can take away heat and cause something to freeze. Now we're going to look at a chemical reaction that, has some kind of unexpected results. Okay, go ahead.
Hello, welcome to our Luminol Light Show. We are looking forward to performing for you today. Now before we go much further, let's explain what we'll be showing you today.
We are going to be showing and explaining luminol.
Now, we're going to talk about the exact chemicals and the exact compounds it'll take to make the luminol.
Oh, that's so boring.
Just kidding. We're gonna show you the reaction instead.
Okay, leave it for the other guy.
Now we will make the luminol. The glow will last 1 to 2 minutes.
Now before that, we are going to be talking about where luminol came from. It was invented by a German scientist named Walter Specht.
He was doing tests on blood with a newly created chemical he had just made, luminol.
He guessed that the luminol would react to blood, but it reacted in a way he did not predict. It reacts to hemoglobins, which contain iron, which is what the luminol reacts to.
The test was so successful that they did tests on other blood samples, and some of those blood samples were over a year old, and still it reacted.
We're actually going to show you video about the reaction.
That in some of them the police uses a chemical to reveal old blood stains that have been removed, and this substance is called luminol. Luminol is used in forensics on crime scenes to detect blood stains with the help of chemiluminescence, which is light production caused by a chemical reaction. So this little molecule here has been a tremendous amount of help for discovering blood traces, and therefore it could lead to successfully closed cases. So we assume we have a bloodstain here. This could be caused by a murder, for example. We assume the murderer will get rid of the traces, so he will properly clean the whole crime scene. So he gets rid of the traces, and just with your eyes you can't really notice that there has been blood. So now we apply luminol, and for some seconds a blue spot will magically appear. This can best be detected under dark conditions, so when you switch off the light. And this process, as I told you in the introduction, is called chemoluminescence. So now we have to go on the level of biochemistry. We have a substance here, and this is luminol. But it's not only luminol. Luminol needs something else, and this is oxidizing agents, such as hydrogen peroxide, which is commonly used there. And together, this mixed substance cannot cause a reaction when there has not been blood. Why is blood important? Blood contains hemoglobin, and hemoglobin contains iron. And this iron complex here, this is catalyzing the reaction of luminol and hydrogen peroxide. So here I show you the reaction in a simplified way. We have luminol and we have our hydrogen peroxide. So in the presence of iron, as you can see here on the blood drop, after several steps luminol will get to a dianion, and when the excited form of this dianion kind of drops to the ground state, it releases energy in form of light. Our luminol will emit a photon, which is in the spectrum of blue light. So essential is the presence of iron complexes, which are contained in our red blood cells. Even if you carefully and thoroughly wash, there will still be remains, and with luminol and hydrogen peroxide you can spray it on the spot, and in the presence of iron complexes we will have a pattern of blue spots. The use of chemoluminescence has been very advantageous and beneficial for the police. And with that I'm out. I thank you very much for watching. Feel free to drop some comments.
Did you guys understand a single thing that just said? Thought so. Oh, you're smart, kid. Anyway, so right now I have some glow sticks for a few people if anyone wants some. Whoa!
Let me have some.
So, fun fact, luminol is actually in glow sticks, which makes it glow.
we know more about luminol.
All right, let's have.
Now that we know more about luminol, let's show you some of ours.
We need the lights to turn off, completely off for this one.
Or for most of them.
We're making more?
Okay.
We know
So,
Peter.
what you just witnessed was the chemical reaction. So as you saw, we took two mixtures and put them together through the spiral tubing. One of those mixtures contains the luminol itself, along with a few other chemicals, one of which is copper 2 sulfate pentahydrate. Long word, don't really need to remember it. But the important thing is it acts like the blood in the reaction. The other mixture is what kind of gets that reaction started. It's the catalyst. So that's what we just put down the tube.
Cool, right?
So now, we have one more batch and we will do it one more time. So we need the lights on completely once more. We will now pour once more.
Now, something kind of interesting, this is what it turned into. It was glowing blue, now it is like a brownish green.
That's kind of gross.
Yeah.
Ew.
That's it for the show. Thanks for coming and bye.
Hold on.
Yeah.
You have a question? Oh, okay.
Okay.
Thank you, though.
Yeah.
All right, that was a fun one. A chemical reaction that produces light. Our next group is going to show you another way to produce light, not by using a chemical reaction in the same way, though.
Hello, everyone. I am Ellis Michael Harding, and these are my associates. We have Anthony. Hello. Matthew. Hi. And last but not least, we have Alex.
Hello.
They will be helping me today in our first scientific demonstration as the League of Extraordinary Gentlemen Seeking Obligatorily Necessitative Fire and Reactive Environments, or, in shorter terms,
On fire!
Now, Canyon, would you be so kind as to get the thing for me? I know. Alex, tell our watchers what we're doing.
We will be recreating an artifact from the Avengers movie called the Tesseract with science.
Correct. Now, as we all know, the Tesseract is an incredibly powerful object, so much so that even our very bad attempt at recreating it has some level of danger. So, Anthony here will be on standby with a fire extinguisher for the sake of safety, just in case our experiment goes horribly wrong again. Matthew?
That was one time.
You threw a flaming paper airplane into a pot of oil. The whole school could have burned down.
It was funny.
Well, now it's a $600 fine. Anyway, where was I? Ah, yes. Anthony will be on standby with the fire extinguisher.
I wish I could have joined this experiment today.
You'll get your chance, man. Now, for the sake of safety, we must also wear these gloves. They protect us from both the hot and the cold of this experiment. Fire and ice, if you will. Now, Alex here will be the one explaining what is happening as we do our demonstration.
Because I actually took the time to read the warning labels on the back.
Pish posh, science isn't fun when you have to slow down and read. Now, finally, and I cannot believe I'm saying this, Matthew will be the one handling the blowtorch.
Hey, I won that draw fair and square.
I know, that's what scares me. Now, let's begin. Lights, please. Yeah, don't look directly at the light. Can we get lots again? Right now, clearly something very interesting has happened. Alex, tell us what happened.
All right, so this reaction is called combustion. The magnesium is taking the oxygen from the carbon dioxide and turning itself into magnesium oxide, releasing a ton of heat and a ton of light. It is so hot that it can actually melt through solid steel.
Interesting. What else can you tell us about magnesium?
So, magnesium is commonly used to make structural alloys for airplanes and helicopters because it is 1/3 as dense as aluminum.
Interesting. I thought it was only for explosions.
And it is commonly used with other metals to make fireworks.
And there we go, back to explosions. Now, where does the name magnesium come from?
Magnesium was found in a place called Magnesia, which is why it is called magnesium.
Wow, this all sounds absolutely fascinating.
It's explosively interesting.
Never again.
All right, I really hope you're enjoying our show so far. We've got one more demonstration for you guys. So hopefully we can end this show with a bang.
Hello, I am Ethan.
I'm Jaden.
Hello, I'm Carter. You might be wondering what this is, what Jaden is doing. Well, since the time of caveman, fire has been interesting and balloons have been fun, so we decided to make fire balloons.
Our fire balloons work very similarly to fireworks. Fireworks themselves were invented in around the 2nd century in China. These fireworks, however, were made of bamboo and created plain black explosions.
I think it's me. All right. Imagine what would happen when these fireworks exploded.
That's why they created fuses.
Colored fireworks themselves were invented in around the 1600s in England. These fireworks were made using certain elements and minerals.
That's kind of what we're doing today. To make these balloons, we will need zinc, hydrochloric acid, and balloons. And then when...
Because hydrogen is very flammable, we couldn't end up just having like a canister or anything of it just sitting around in our classroom, sadly. So we had to make our own, of course, which is just using the materials that Ethan explained. And, well, I'd say we should probably start exploding these.
Yeah. We will need to tie the balloons up like this before we let it go, and... Yeah, balloon. Oh, wait, turn up the lights, like all that. It's better when it's dark. Okay, time for the second one. Also, cover your ears. Okay, Carter, you're next. You're up next, Carter. I'm the last. I want to do the last one.
There's no one to test the wall. This is actually one sort of
Ethan. Thank you for having us. We're not doing that. We've learned better.
All right, everybody. Thank you for coming to our show. Do we have any final questions before we leave? Oh, right here. Oh, that's a great question. How many times have we failed on just one experiment? Well, we had one group that was trying to find an experiment to do that would work, and they had to go through 3 different experiments before they found a good one. Their first 2 failed on them, and they couldn't get them to work as a demo for a show. So there's a lot of trial and error and a lot of failure in science. But every time we fail, we learn something new and we grow from it. Yeah, back here. Yeah. How come fire creates smoke? So the smoke you're seeing from the fire is all of the ashes that were left over. But the hot air picks up those ashes and they rise up, and that's what we see as smoke. Here, a question from the back here in the red. Yeah. Which acid experiment? The first one with the styrofoam? Yeah, that was acetone. It's actually not an acid. It's paint thinner. It's used in fingernail polish remover. Yeah, standing up. Yeah. The chemical from the first experiment was liquid nitrogen. Now, there's nitrogen gas in the air all around us, and we breathe it in all the time, but it's not bad for us. But it's not a liquid at room temperature, it's a gas. So you cool it down to like -200 degrees, and you can use it to freeze things. Okay, right here. Why did the money not burn? So the money was dipped in a mixture of water and alcohol. The alcohol will burn, but the water soaks the money, and the water prevents it from burning. So the alcohol burns off, but the wet money is still safe. What was that? You mix them together, and then you put the money inside the mixture. Yeah. Have we ever blew up a pumpkin? We were trying to blow up a pumpkin, one of our groups, with the elephant toothpaste, but we couldn't get a strong enough elephant toothpaste to do that. We tried to, though. We really wanted to blow up a pumpkin today. Okay, up in the back. Yeah. Yeah. So to make the elephant toothpaste very strong, you need a high concentration of hydrogen peroxide, and you can't buy that at the store. You can buy hydrogen peroxide at the store, just not the strong stuff that you need to make a good elephant toothpaste. Yeah. All right, one more question over here. Yeah. Yeah, so that chemical they used is called luminol. And the luminol reacts with the iron in your blood. Yeah. Very good. All right, well, I hope you had a great time at our show today. Oh. Okay, I hope to see you guys at the high school in a couple of years, and I hope you bring this enthusiasm and excitement for science with you. We've got a lot of cleaning up to do, so thank you all for coming, and I hope you have a great afternoon.